Hello everyone, welcome to my YouTube channel. So today I am going to discuss an interesting linear algebra problem. Mainly I will discuss the properties of the linear operator. It is important because this type of question is asked in many competitive exams like NET, GATE, JAM and also in TFR. So, T be a linear operator from set of all real n cross n matrix to set of all real n cross n matrix. T of B is basically AB, where A is a fixed n cross n matrix. It is quite obvious that T is linear. You can easily check this. Now to discuss the property of T, we need to know the matrix representation of T. Now, since T is linear, so matrix representation of T is completely determined by T of Eij, where Eij be the n cross n matrix with all entries 0 except ijth entry being 1. Because the set of all Eij where 1 less equal to I, j less equal to n forms a basis for set of all n cross n matrix with real entries. Okay. So since this forms a basis, so matrix representation of T is completely determined by this matrix representation of T is completely determined by the values of T on this basis matrix. Okay. So it may be difficult to understand for arbitrary n. So let's start with n equal to 2 so that you can easily understand it. Okay. So let n equal to 2. And I have fixed a matrix A. Say A is basically A11, A12, A21, A22. This is the fixed matrix A. Now basis of M2 cross 2R is basically set of all Eij where I and J belongs to 1, 2. This set. So I have 4 matrix in the basis. So say 1 0 0 0 0 1 0 0 0 1 0 0 0 0 0 1. I assume this is the ordered basis of M2 cross 2R and observe the order. First I take 1 in the first entry, then I take 1 in the first column second entry, then I take 1 second column first entry, then I take 1 second column second entry. Why I choose the basis in this way you will understand later, but it is important to choose in this way to get a nice form of matrix representation of T. Now to observe the matrix representation of T, we define an isomorphism between M2 cross 2R to R4. I mean the matrix is just like, I will observe this matrix is just like an element of R4. Okay, so in this way, here A11, A12, A21, A22 be the matrix, then I just write down these columns. These columns, first I write down first column, then I write down second column in this way. Okay, so I will get an element in R4. Okay, now I just compute the value of T on the basis vectors. I mean basis vectors in the sense basis matrix. Okay, so T of 1 0 0 0 is basically this one, so I will get A11, A21, 0 0. Similarly, T of 0 0 1 0, I will get this. T of 0 1 0 0, I'll just, it is just a matrix product, nothing else. Okay, so it is obvious. Now what is the matrix representation of T? So this one the first basis matrix, right? So T of these must be the first column vector of the matrix representation of T. So first column vector must be this one. Now this one is basically isomorphic to R4. We already know it, right? So A11, A21, 0 0 is basically isomorphic to this. So my vector looks like A11, A21, 0 0. This one, okay? So T of 1 0 0 0, this matrix will be my first column in the matrix representation of T. Okay, so this one. Similarly, 0010 is basically this. So since 0010 is basically this, so I have A12, A22, 00. Similarly, T of 0100, I have 00, A11, A21. And similarly for T of 0001, I get 00, A12, A22, which is 00, A12, A22. Now observe that T is basically a 4 cross 4 matrix. So it is definitely true, because why? We know if T is a linear operator from V to V, if dimension of V is K, then T matrix representation of T is basically K cross K matrix. Now here dimension of the vector space is n square, right? Because M n cross n r, I mean set of all n cross n matrix with real entries, has dimension n square. This is a vector space has dimension n square. So matrix representation of T must be n square cross n square. So here matrix representation of T is basically n square cross n square. Okay. So here n equal to 2, so matrix representation must be 4 cross 4 matrix. So I get 4 cross 4 matrix here. Okay. Now observe this matrix representation of T has a nice property. Why? This matrix representation T is basically A in the first block matrix. This one A, this is 0, this is 0, and this is A. It's nice, right? So you have block matrix A in your diagonal and all the other block matrix as 0. It is interesting. Now try to generalize this. I mean, I will do it for arbitrary n. Okay. So say now take the basis matrix of E. I mean take the basis matrix of M n cross n r. That is Eij, right? Where Ij belongs to the set 1 to n. So and take A be the fixed n cross n matrix with entries Aij. Okay, so here it is A. T of Eij, and here it is Eij, where say this ijth entry is 1 and all the other entries are 0. Now if we do the product, what we get? We know that the first position of this matrix, product matrix, must be the dot product of first row and first column. Second, first row, second entry must be product of first row, second column. That means Bijth entry, if we say there's entries of this matrix is basically Bij, that means Bijth entry is basically ith row and jth column. Ith row of this matrix and jth column of this matrix dot product, right? So since all the other entries except ijth entry of this matrix is 0 and only the ijth entries is 1, so after doing product, what we get? We get all the other entries at 0 except that jth column must be non-zero and entries of jth column is a1i, a2i, dot dot dot, ani, and all the other entries are 0. So this is n cross n matrix. So I just compute Teij in this way. Okay. Now say basis of m n cross n r, we just make a order in this way. So let's take the order. See the order. First E11, E21, E31, dot dot dot, En1, then E12, E22, dot dot dot, En2, then in E13, E23, dot dot dot, En3, and similarly so on. And finally I get En1, sorry, E1n, E2n, dot dot dot, En. Okay. So why do we take it in this way? This is also interesting. We'll see it. Okay. So this is also interesting, right? Now our order is basically in this way. So if I observe the indices, I just first take 1 1, then 2 1, dot dot dot, then n1, then again take 1 2 2 2, dot dot dot, n2, and similarly go so on. And in last column I take 1 n 2 n, dot dot dot, nn. So in this way. Okay. So column wise, I mean indices must be you just observe the indices because here it is matrix and here it is just the entry. So I just tell you to observe these indices. Okay, so here it is in this way. So I just take in this way, right? So this is the ordered basis I just take for M n cross n R. Now if you observe that each ijth matrix in this ordered basis, ijth matrix is in n into j minus 1 plus ith position. Why? Because observe that, say here somewhere it is aij entry. Okay, I just observe aij entry. Then before this I have j minus 1 column, because aij must be j inside jth column. So I have j minus 1 column. So each column contains n matrix, right? For each column we have n matrix. So j minus 1, for j minus 1 columns we have n into j minus 1th entries. And since it is ijth entry, that means we start from 1 2 3 dot 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 I. So total I have n into j minus 1 plus ith position. Eij is n into j minus 1 plus ith position in this. Okay, now what will be our matrix representation for T? I just compute T of E11, and then I write down it as the first column of my matrix representation. I mean the T of E11. I just write down it as a linear combination of these vectors and the coefficient. The coefficient here I just tell it as a vector because it's a matrix. Okay, so TE11 is basically linear combination of this matrix, and the coefficient of that combination must be our first column, right? Now T21 is basically also a linear combination of this matrix, and this will be our second column. Similarly Tn1 will be our nth column. Now what about Te of 1 2? This will be our n plus 1th column. What will be our T22? This will be our n plus 2th column. What will be our Ten2? This will be our 2nth column, and similarly so on. So if we compute it, what we'll get? We'll get the matrix representation of T is just like these forms, where the diagonal entries are blocks, where blocks are basically A matrix and all the other blocks are 0. And this is a n square cross n square matrix. This is a n block. This is a n block. And so on. This is last one is n block. This is a diagonal, right? So here is a n block, n block, n block, and I have n times. That means n square time. So this is n square and also this is n square. So it is a n square cross n square matrix. So we are generalizing this, right? So since we already get the matrix representation of T, now it is easy to discuss the properties of T. And observe that the properties of T is completely depends on the properties of A. Okay? Say rank of T. Rank of T is basically n into rank of A. Why? Here I have n blocks which is A matrix, and all the other blocks are 0, right? So here for this part rank is rank of A, for this part is rank of A, for this part rank is rank of A. So total rank what? N into rank A. Similarly trace T is basically, because here it is trace of A, so it is n times, so n into trace of A. Determinant of E is determinant of A to the power n, because this, for this matrix I have determinant of A, this is determinant of A, and I, to get determinant of T I have to product determinant of A n times. So this is determinant of A to the power n. Now characteristic polynomial of T is basically characteristic polynomial of A to the power n. It is obvious. Now what about minimal polynomial T? Minimal polynomial T and minimal polynomial of A both are same, because if minimal polynomial of A is basically Px, then P of A equal to 0, then this part 0, this part 0, all the parts are 0, and other terms are already 0, so P of T is also 0. That means minimal polynomial of T and minimal polynomial for A both are same, and eigenvalues of T and eigenvalues of A are both are same. It's obvious. Then and T is diagonalizable if and only if A is diagonalizable. Because if A is diagonalizable, then we know that minimal polynomial of A must be product of distinct linear factors, and since minimal polynomial of T and minimal polynomial of A both are same, so minimal polynomial of T also have product of distinct factor, linear factor, so T is also diagonalizable. Okay, so I just discussed the interesting properties of this linear operator. And in JAM exam as well as in GATE exam, there was a question like to find out the rank of T, so which is basically n into rank of A. But not only rank of T, if you have ask any kind of question related this matrix T, I mean related this operator T, then you can easily say, because the matrix representation of this operator T looks like this. All the other blocks are 0 except the diagonal blocks are A. Okay. Okay, so thanking you. Yeah. So I hope you can understand it easily. Okay. So these are the properties of this interesting linear operator. Okay.